Wipe it clean first, and we dip it back in. Pull it out slow, keep it level.
Most people think thicker oil equals better protection. It feels logical. If 20 is good, 30 must be safer. More cushion, more strength, more insurance. That's the belief. We tested it, and in one of our vehicles, going thicker actually made things worse. If you've searched 0W-20 versus 0W-30 comparison, asked is thicker oil better, or wondered which engine oil should I use, this is going to recalibrate how you think about viscosity. Because we didn't rely on forum debates. We ran controlled mileage, logged oil temperature behavior, tracked fuel economy, measured oil pressure, recorded oil consumption, and sent samples to a lab for used oil analysis. And what we found shows exactly where most drivers are right and exactly where they're confidently wrong. Stay with me, because by the end, I'll break down 3 real-world driver profiles where thicker oil helps and one where it quietly loses the argument. Let's start with a quick reality check. Both 0W-20 and 0W-30 flow extremely well when cold. That 0W rating means both perform well during cold starts. The real difference happens once your engine reaches full operating temperature. The second number, 20 versus 30, determines how thick the oil remains at around 212 degrees Fahrenheit and beyond. That thickness affects fuel economy, oil pressure stability, film strength under load, oil consumption, and long-term durability. Oil performance is about system balance. Thicker oil does not automatically create protection. It changes mechanical trade-offs. Now let's talk about how modern engines actually use oil. Engine oil today does far more than reduce friction. It forms a hydrodynamic wedge between bearings and crank journals. It removes heat from pistons and turbochargers. It operates cam phasers hydraulically. It maintains timing chain tensioners. It suspends contaminants. It prevents corrosion. When you start your engine, metal surfaces briefly operate extremely close together before full oil pressure builds. Those first seconds matter. Oil flows through calibrated galleries designed around a specific viscosity range. Oil pumps are engineered for expected resistance. Variable displacement pumps adjust pressure based on that resistance. Change viscosity outside the intended design range, and you alter flow timing, pump load, and hydraulic response speed. That's fluid dynamics. Here's something almost nobody talks about in oil debates: bearing clearance. Every engine has specific clearances between crankshaft journals and bearings. Those clearances determine how oil forms a pressurized wedge that keeps metal separated under load. Modern engines typically use tighter clearances than engines from the 1990s. Tighter clearance means oil does not need to be as thick to maintain separation during normal driving. That's one reason manufacturers confidently recommend 0W-20 in engines that once used 5W-30. Oil pump design, oil gallery routing, and bearing clearance are engineered together. Viscosity is not chosen in isolation. Copying advice from older engines does not always translate to modern designs. Engineering evolves. Oil strategy evolves with it. Now let's answer a common question. Does thicker oil increase oil pressure? Yes, but that does not automatically mean better protection. Thicker oil increases resistance. Resistance increases pressure readings, but pressure is not the same as flow. Flow volume carries heat and maintains lubrication coverage. Higher pressure with reduced flow can increase pump load and slightly lower efficiency. Protection comes from maintaining a stable oil film while preserving proper circulation. Balance matters. If you look at an engine oil viscosity chart, you'll see viscosity sharply drops as temperature rises. Cold performance matters at startup. Hot performance matters under sustained load. 0W-20 and 0W-30 behave similarly when cold. They separate more once hot.
Under shear stress, like bearings spinning thousands of revolutions per minute, oil temporarily thins. That's why high-temperature, high-shear ratings exist, and that becomes important under stress. Now let's talk about the test. We used 3 vehicles: a 2022 Toyota Camry, a 2018 Ford EcoBoost turbo sedan, and a 2011 Honda CR-V with 132,000 miles. Each vehicle was manufacturer approved for both viscosities, depending on climate. We ran 0W-20 for 4,000 miles, then 0W-30 for 4,000 miles. Same oil brand line, same drivers, same routes, same fuel. We tracked cold start oil pressure rise, fuel economy, high temperature oil pressure, shear stability, oil consumption, and lab wear markers. No assumptions, only measurable behavior. Cold start is where most wear happens. Up to 70% of total engine wear occurs during startup. In temperatures between 28 and 35 degrees Fahrenheit, 0W-20 stabilized oil pressure roughly 7 to 10% faster. That advantage disappeared once heat entered the equation. In the Camry, thinner oil aligned perfectly with design intent. In the older CR-V, the difference was negligible. Under startup conditions, thinner oil clearly performed as engineered. But startup is not the entire story. Now let's talk about fuel economy. Across all vehicles, 0W-20 delivered about 2.3% better fuel economy. If you drive 15,000 miles per year at 28 miles per gallon, that's roughly 535 gallons annually. A 2.3% gain equals about 12 gallons saved. At $4 a gallon, that's around $50 per year. Over 150,000 miles, that compounds. Manufacturers moved towards 0W-20 because modern engines use roller cam followers, tighter piston ring packages, improved machining tolerances, and variable displacement oil pumps. Reducing internal drag through optimized viscosity lowers pumping losses, improves warm-up efficiency, reduces emissions, and enhances hydraulic precision. The shift was not arbitrary. It was system-level engineering. Now let's talk about high-temperature, high-shear. You'll often see it abbreviated as HTHS. High-temperature, high-shear viscosity measures oil behavior at roughly 150 degrees Celsius, about 302 degrees Fahrenheit, under extreme mechanical stress. These are conditions similar to what rod bearings, main bearings, cam lobes, and turbocharger bearings experience at high engine speed. Under those conditions, oil is not calmly flowing. It is being compressed, stretched, and sheared thousands of times per minute. Viscosity temporarily drops under that stress. That is called shear thinning. Oils with higher HTHS ratings resist thinning more effectively under sustained load. 0W-30 typically has a slightly higher high-temperature, high-shear rating than 0W-20. On paper, that difference looks small. Under sustained heat and load, it becomes measurable. For everyday commuting, most engines rarely stay in those conditions long enough for that difference to matter. For high-load, high-temperature driving, it can matter. That is the line. Now let's talk about the turbo stress test. We pushed the EcoBoost hard. Sustained boost, long highway pulls, oil temperatures climbing past 240 degrees Fahrenheit. At that point, your turbo shaft is spinning at over 100,000 revolutions per minute, suspended entirely on a microscopic oil film. That oil film is the only thing preventing metal-to-metal contact. This is where thinner oil started losing the argument. And this is the moment thicker oil finally earned its reputation, but only under very specific conditions. Under sustained load, 0W-30 maintained 5 to 8% more stable oil pressure. Viscosity retention under shear was slightly stronger. Iron wear markers were marginally lower. Not dramatic, but measurable. Under extreme thermal stress, thicker oil held film stability more confidently. If you are searching for the best oil for hot weather or running a turbocharged engine in very high ambient temperatures, this is where 0W-30 builds a mechanical case. But here's what matters. That advantage did not appear in city driving. It did not appear in moderate climates. It showed up under sustained heat and load. Context decides advantage. Now let's clarify what the lab data actually tells you, because this is where many drivers misinterpret results. We monitored iron, copper, aluminum, viscosity retention, and fuel dilution percentage. Iron reflects cylinder and valve train wear. Copper reflects bearing wear. Aluminum reflects piston wear. Under moderate driving, wear differences between 0W-20 and 0W-30 were minimal. Under sustained heat, 0W-30 retained viscosity slightly better and showed marginally lower iron. But the biggest wear difference we observed was not viscosity related.
It was interval related. Stretching oil change intervals too long created significantly higher wear markers than switching between approved viscosities. Fresh oil versus neglected oil produced the largest measurable impact. That is mechanical reality. Now let's talk about high-mileage engines. Many drivers compare high-mileage engine oil versus regular oil and assume viscosity alone is the difference. It is not. High-mileage oils often include seal conditioners, oxidation stabilizers, and adjusted additive packages. Seal conditioners can slightly swell aging rubber seals. That can reduce minor seepage and slow oil consumption. In our 132,000-mile CRV, 0W-20 consumed roughly half a quart more over the interval. Switching to 0W-30 reduced oil consumption and slightly increased hot idle oil pressure. This is why many drivers believe thicker oil fixed their engine. Because in aging engines, it often stabilizes pressure and reduces burn-off. But thicker oil does not repair worn bearings. It adjusts operating behavior within widened tolerances. That distinction matters. There is also a scenario where thicker oil quietly works against you. If you run thicker oil unnecessarily in a modern tight clearance engine, cold start circulation slows slightly. Oil pump resistance increases. Efficiency drops marginally. Hydraulic timing response can shift. Short-trip drivers in cold climates benefit more from rapid oil flow than extra hot load thickness. Engines with oil-controlled cam phasers depend on precise hydraulic response timing. Viscosity influences that response speed. In our Camry, switching to 0W-30 showed no measurable durability improvement and a slight increase in parasitic drag under normal commuting conditions. This is where thicker oil started losing the argument for that specific engine. Not because thicker oil is bad, but because it did not align with how the engine was used. Now consider the compound effect of small differences. A 2% efficiency change sounds small. A 5% oil pressure stability difference sounds small. But engines operate thousands of hours over their lifetime. Small differences compound. If you lose 2% efficiency unnecessarily over 150,000 miles, that is additional fuel burned and additional pump load year after year. If you operate a turbo engine under sustained heat without adequate film stability, that is incremental wear multiplied over time. The real question is not which oil sounds stronger. The real question is which oil optimizes your engine's operating pattern over the long term. That shift in thinking changes everything. So why did manufacturers move towards 0W-20? Yes, emissions regulations influenced the shift, but engineering evolution made it possible. Modern engines use tighter bearing clearances, advanced cylinder wall finishes, improved piston ring geometry, variable displacement oil pumps, and optimized oil routing.
Reducing internal drag through optimized viscosity lowers pumping losses, improves warm-up efficiency, reduces emissions, and enhances hydraulic precision. The shift was not arbitrary. It was system-level engineering. Let's simplify this into 3 driver profiles. Driver 1, the efficiency commuter. Modern engine, moderate climate, mostly city driving. 0W-20 aligns with design intent and maximizes efficiency. Driver 2, the heat and boost driver. Turbocharged engine, high ambient temperatures, sustained highway load. 0W-30 adds thermal margin and improves high load stability. Driver 3, the long-term keeper. 120,000 miles or more, mild oil consumption, moderate climate. 0W-30 may stabilize wear and reduce burn-off. 3 drivers, 3 optimized strategies. There is no universal winner. This debate persists because older engines required thicker oil. That advice became cultural. Heavier feels stronger, thicker feels protective. But lubrication physics does not follow emotion. Protection depends on maintaining a stable oil film under actual operating conditions. Optimization is contextual. Here's the real conclusion. The biggest performance difference we observed was not 0W-20 versus 0W-30. It was fresh oil versus neglected oil. Engines rarely fail because someone chose one manufacturer-approved viscosity over another. They fail because maintenance discipline slips. Viscosity is optimization. Maintenance is survival. What do we personally run? Modern tight-clearance daily drivers, 0W-20. Turbocharged engines in sustained heat, 0W-30 when conditions justify it. High-mileage engines with minor consumption, situational, often 0W-30. Not because it feels stronger, because measured stress data supported it. Most people argue, we measured. If you prefer engineering over internet myths, data over emotion, and measured trade-offs over blanket advice, subscribe. Because we test what most channels speculate about. Now ask yourself, what engine do you drive? What climate do you live in? What mileage are you at? And are you running what feels safest or what actually fits your context?